estarem aqui e pontualmente. Isso é muito perfeito, mas sejam todos bem-vindos a esse webinar com o tema Soluções de Telemetria de Rotor para a da Accumetrics para máquinas rotativas. Eu me chamo Rofilda Pinheiro, faço parte da equipe de marketing da MTS e em nome de todo o nosso time, eu gostaria de agradecer por vocês estarem aqui com a gente hoje, fazê-los muito bem-vindos. Espero que vocês possam ter uma experiência incrível e tirar todas as dúvidas que vocês têm. Também a gente vai todo o suporte que vocês precisam. Eu estou aqui e a Aline de Lira também tá para ajudá-los, tá bom? E a MTS, ela é representante exclusiva da Accumetrics no Brasil. E a Aline Lira é a vendedora responsável desse produto que nós iremos falar hoje aqui. E que também está presente no webinar. E, então, para o suporte mais técnico, vocês podem entrar em contato com ela. E no final, eu posso estar enviando o contato dela também aqui no chat. Mas vamos lá, vamos começar. Hoje nós temos o apresentador Paul Jarrold. Desculpa se eu não estou pronunciando seu nome direito, certinho, mas eu vou ler sua biografia, né? Dar uma introdução do Paul para a gente. Paul Jarrold é engenheiro elétrico e gerente de desenvolvimento de negócios da Accumetrics, com 17 anos de experiência em sistemas de telemetria para monitoramento de grandes equipamentos rotativos. Paul possui um bacharelado pela East Coast Polytechnic Institute, além de 5 anos de experiência trabalhando nas Forças Armadas dos Estados Unidos, com equipamentos de rádio e comunicação. Especialista em sistemas de telemetria de falha à terra, realizou instalação e comissionamento no local de sistema de telemetria de falha à terra em todo o mundo. Então, essa foi uma introdução um pouquinho do Paul para a gente. Então, a gente vai dar início a esse webinar. Por favor, eu só gostaria de pedir gentilmente que todos possam verificar se seus microfones estão desligados, eu acredito que todos sim. E essa reunião, como a Aline deu uma introdução um pouquinho no começo, ela está sendo gravada e a gente vai disponibilizar o link dela no nosso YouTube. Eu vou mandar para vocês no grupo que a gente tem no WhatsApp também. E aqui, depois no e-mail, pessoal, quem quiser pode entrar em contato comigo. E outro detalhe também é que a reunião ela estará em inglês. Então, para todos que desejarem traduzir, o Teams ele tem uma opção muito legal que vocês podem traduzir e transcrever o webinar para que vocês possam ler em português. Então, aqui no Teams de vocês tem a opção dessas 3 bolinhas, escrito mais. Eu não sei se todos conseguem ver isso, mas vocês podem colocar em idioma e fala e mostrar legendas ao vivo. Então, vai ser legendado para vocês em português. Bom? É isso, pessoal, perfeito. Qualquer dúvida que vocês tiverem, eu vou estar aqui para auxiliar vocês. Vocês podem mandar no chat, a Aline também está aqui. Então, agora eu passo a apresentação do webinar para o Paul e até mais tarde. Até logo. Muito obrigada.
Paul, go ahead, please.
Okay. Hello, everyone. Thank you again for taking the time to join this webinar with us. I'm going to share my screen now, and I'm going to start presenting the topics we're going to discuss today on rotor ground fault monitoring, as well as temperature monitoring for industrial motors. So I'm going to go ahead. Please let me know if you are seeing my screen.
Yeah, we can see.
Okay, fantastic. So we'll jump right in here and get started. I envision this going for about 45 minutes, and then we'll leave 10 to 15 minutes at the end to answer any questions that anybody might have. So today we're going to discuss Accumetrics digital telemetry solutions for rotating machinery. So it's going to be an introduction on ground fault detection on generators with brushless exciters, as well as rotor temperature monitoring for large industrial motors. So Accumetrics, so we've been in business for more than 3 decades now. We're a global leader in providing telemetry systems for ground fault protection, both for OEM suppliers, large suppliers like GE, Siemens, Andritz, ABB, Alstom, as well as large motor manufacturers to test and provide them with monitoring capability on their equipment. So we employ short-range wireless technology to communicate between a rotor-mounted transmitter that's spinning on the shaft and also provide induction power across a wireless communication link to power our electronics that are out on the rotating shaft. that communication comes across a small air gap to the non-rotating side, where we provide the outputs to the operator. So a little background on myself. I've been with Accumetrics now for 17 years. Prior to coming to Accumetrics, I served for 5 years in the United States Marine Corps with some background in radio communications equipment while serving in the military. I'm the business development manager for the company. I've worked my way up through the company and have provided on-site installation support, commissioning of systems for site visits at customer sites worldwide. So this is a basic block diagram.
Hey, Paul.
Yeah,
The slides aren't changing for us.
they're not. Okay.
Yeah, like if you moved on to your bio slide, we're still on the title slide. We actually still see the slides on the left. It's not in like presentation mode or anything.
Yeah, I believe the problem is that you are not in presentation mode yet.
How about now? Are you seeing them change now?
Yeah.
Okay.
Yep.
Thank you.
Now you're on you. Oh, now you're on what is rotor telemetry.
Okay, great. That's where we left off. Sorry about that.
Okay.
So this is a basic concept of how all of our telemetry systems work. Again, today's discussion, we're going to be talking about rotor ground fault monitoring and temperature monitoring for large industrial motors and generators. But we work in all different sorts of industries, aerospace and defense, automotive industries, pretty much any type of rotating equipment you can think about where a customer may want to monitor a different type of sensor that's rotating shaft. That's what we specialize in. So we take a sensor parameter, in this case, rotor ground fault, and a resistance measurement or temperature from RTD sensors. We can also interface to things like thermocouples, accelerometers, pressure sensors, any type of sensor a customer has. They've got this sensor, right, and they want to collect data off of a rotating shaft. And it's always the challenge. Well, how do we do that? We don't want to use slip rings or any type of mechanical contact. We want long-term, reliable, wireless communication. That's where we specialize in. So we take that sensor parameter, it gets connected right to the rotating digital transmitter, which would be mounted on the shaft and spinning with the equipment. And then that rotating transmitter essentially has a hoop of wire that forms a rotary transformer connection between the rotor and stator. And so that, as long as that's in close proximity and coupled close by to the stationary hoop, we're communicating data off of the rotating shaft. So we bring data off the rotating world through one hoop of wire to a stationary hoop of wire. And then that gets connected via cable to our digital receiver. And then we provide the outputs to the customer from our receiver unit. The outputs can come in forms such as relay contacts, 4 to 20 current loop outputs, or a straight digital, like a Modbus TCP digital output. And then inside our radio receiver unit, we're creating an induction power signal that comes back the other way and goes across that same air gap from the stator now back to the rotor and powers our electronics out on the rotor. So all of our systems are completely independent and self-powered. We don't require battery power or power from the rotating shaft, like field voltage contact or anything like that. Completely independent system that's very robust and reliable. So why customers would want to use telemetry? I mentioned some in the previous slide about getting away from things like slip rings or optical-based communication sensors or some type of other mechanical device used to contact a rotating shaft. All of our stuff is wireless. A lot of customers use it to troubleshoot things like premature vibrations, failures, and just overall performance issues on their rotating equipment. It helps them provide better machine design, but also can help them predict for failures on their rotor components. So in this discussion, those failures we're going to be talking about primarily are going to be ground faults, and we're going to get into that next on what that means. So a rotor ground fault is a situation where your field ground fault is when insulation breaks down between the generator rotor windings and the rotor itself. So the windings are a bunch of copper bus bars that wrap around a cylindrical generator rotor and create three-phase AC electric power. Those windings need to be isolated from the rotor itself because they carry a large amount of electrical current. And there's always a risk that if you have a ground fault, what can happen is you can create a shorted path or a path of least resistance from the field windings to the rotor itself. And that, in that case, as you can see the image here on the right, that caused some damage where it actually melted the rotor field windings together and caused a situation where the customer had to stop their generator and investigate the problem and troubleshoot and fix the problem. So it's a significant issue in power generation, and customers are very concerned about rotor ground faults. So this is an example of what the field bus bars look like when they are installed inside of the generator rotor. There are grooves cut on the cylindrical generator rotor and have many different stack-ups of these field bus bars or field windings inside the rotor. Those are insulated from each other with thin pieces of insulation between each winding, but there's also a slot liner material, which is a non-magnetic, excuse me, material that protects the current flowing through these copper bus bars from leaking over and causing a short between the rotor forging itself. So if this material gets worn down and causes a break or a hole in the material, now the current that would be passed along normally through the copper bus bars will leak out and start to cause damage of the rotor itself. If you get two faults that develop along the rotor, that is a very significant or very damaging case where now all your current that's supposed to be flowing through the field windings is now diverted directly into the rotor forging itself. You can superheat the rotor, cause it to warp and have massive vibration issues, as well as just burning and damaging from that current arcing into the rotor. So faults can occur in the slot liner. They can occur in the retaining ring on each end of the cylindrical rotor. There's different areas where that can happen. The main thing is that you need to have a system that's able to monitor the value of resistance in that copper bus bar over a long period of time. And you can predict when a ground fault's going to happen when you see the resistance of those windings drop. So this is an example, a picture of what a cylindrical generator rotor would look like. So in that first slide that I showed for the ground fault, that fault occurred on the end of the rotor between the field windings here, an area that they usually would put what they call a retaining ring or retaining cap on each end of the cylindrical rotor. And that's where that one customer had a fault happen. However, a fault can also occur somewhere along the path of the rotor itself. Anywhere in any of these slots that are cut into the cylindrical rotor, a fault can happen. And if you have two faults develop, that's the worst case scenario now, where all your current is diverted into the generator rotor and can cause really significant damage to the machine. So here's another picture on the right to show you where that damage happened on a customer's machine, where the ground fault happened inside the slot and caused burning of the generator rotor. And the customer had to pull the unit offline and repair the damage. So it's a massive cost to utilities because not only are you not creating power to provide to the grid and essentially to sell your electricity, you're also having to pull your machine down in an unplanned outage, and can cause a massive amount of cost to the utilities when they have unplanned outages. So again, two faults are the most severe case, and that can result in the biggest amount of damage. However, a single point fault can also be damaging, like I showed where the fault happened underneath the retaining ring. So this is some more damage that's happened to customers' machine due to a catastrophic ground fault, where now all the rotor has to be pulled out of the machine, all the windings have to be removed, and in this case, the customer is able to cut and re-weld in some slots for those field windings, which is a massive cost to them. So again, most gas turbine generators use a cylindrical style rotor like the pictures I'm showing here. So it consists of that cylindrical rotor and the forgings that are slotted inside that rotor to help install the copper bus bars or copper conductor field windings. And the turns are all layered in that slot, insulated from themselves and primarily insulated from the rotor. You don't want the current that's supposed to be generated around the cylindrical rotor getting away from those bus bars, because that can cause all that vibrational stress, burning, heat, expansion and contraction stress, and real damage to the rotor forging. So this is a case where a customer had a single point fault. So a double ground fault is the worst case scenario. However, a single point fault can also cause damage to the retaining rings. In this case, on each end of the cylindrical rotor, the fault happened and burned into the retaining ring, causing the unit to have to be shut down. And that's what some more images of what that damage looks like underneath that retaining ring. Okay, so we're going to talk next about brushless exciters versus brushed exciters. So generator rotors require excitation voltage to power the rotor windings. Essentially, you can think of it as like the power source or power supply for the generator rotor field windings. And most generation facilities have two types of excitation systems. There are brushless exciters and there are brushed or static exciters. So our focus at Accumetrics is to support the brushless generator market. A lot of the new machines that are being built from many of the manufacturers out there are in fact brushless. Brushed tend to be an older technology. The brushed or static machines were kind of an older technology. A lot of the manufacturers are going away from brushed and moving into the brushless world. In a brushed exciter, you have direct access to the DC field. That's brought across some static brush systems. So it's a mechanical contact to bring DC power to the generator rotor itself. Where on a brushless system, you don't have direct access to the DC field. So it's different from the brushed unit. So our focus at Accumetrics is supporting the brushless exciter market, both for end users and machines that are installed in the field, as well as new machines being built at the factory level. So this is an example of a brushed or static exciter. You can see the brush rigging and slip rings that are on the generator rotor. So there is direct access here to the DC field voltage. And in these systems, oftentimes there is a relay contact that is looking for current to flow between either the plus or minus of the DC field and rotor ground. And if there is current flowing, it'll close that relay contact to let the customer know they've got a ground fault somewhere in their field windings. So there is no need for an Accumetrics wireless system in this case, because you have that direct access to the DC field source. However, on a brushless unit, you don't have that direct access. They bring across AC voltage, which is induced on the brushless exciter. That is converted back into the DC field voltage through some diode wheels or silicone rectifiers that are mounted on the brushless exciter that convert the AC voltage back to DC voltage to be fed into the generator field windings. So on a brushless exciter, there's no means to gain direct access to that DC field. So it's a little more complicated to monitor for ground faults on a brushless exciter. That's where Accumetrics comes in, and that's what we specialize in doing. So we're going to talk about our main product to monitor for ground faults. It's our AT8000 EFRM system. EFRM stands for Earth Fault Resistance Monitor. It makes a continuous quantitative measurement of the field insulation resistance, the excitation voltage, and we also have a feature in our system called location factor, which is a design troubleshooting piece of our equipment that allows you to predict approximately where in your generator field the fault has occurred. The system provides the customer with two ground fault alarm outputs. So we have a warning alarm output that will trip a relay and close once the value of that field resistance drops below 100 kilo ohms. And then we have a secondary alarm, which is our ground fault alarm, that will close a relay contact and trigger an alarm when the resistance value drops below 2 kiloohms. So in a healthy generator rotor that's just been rewound, let's say, or newly built or newly renovated, your resistance value of all those copper bus bars is going to be very high resistance value in the megohm range, maybe 10 or 50 or 80 megohms. And that's good. That means you have a healthy generator rotor based on the value of resistance of those field windings. Over time, as a fault develops, that resistance level is going to drop because you're losing your current flow from the windings, and it's going somewhere else in the steel of the machine and the rotor forging. So you're very concerned in a power generation facility with low values of resistance. High values are good, low values are very bad. So our system is designed to give you a warning alarm to let you know you're dropping at a low value, however, not at a ground fault state yet. But then once you continue to drop in value, more current is lost, you will trigger the ground fault alarm. And then lastly, we have another relay that's called our malfunction alarm. This will trigger if there's an issue with the telemetry system. So if the telemetry system ever loses power, or there's misalignment between the rotor and stator components, or the cable gets damaged or disconnected in any way, that will trigger a malfunction alarm, allowing the user to know that they're not being monitored and there's an issue with the telemetry system itself. And then lastly, a big advantage of our system is that we provide you an ability to trend the value of that field resistance and field voltage over time using 2 channels of analog outputs that are a 4 to 20 current loop output. So that oftentimes gets connected to a customer's DCS or control software and allows the customer to predict and kind of trend the value of that resistance so they can monitor it over many years and look for that value of resistance to slowly drop over time. So the EFRAM system comes in 2 product sizes or 2 product packages, the mid shaft system and the end of shaft system. So we're going to discuss our mid shaft system first. This system is designed for larger brushless exciters. Usually we see these on like a Siemens Westinghouse type of brushless exciter, very large machines, maybe 500 megawatts or greater. In those machines, they induce the field voltage using a permanent magnet generator on the end of the exciter, and we don't have direct access to the field windings on the end of these larger exciters. So we have designed our mid-shaft telemetry system that is used it's a split collar design that's designed to bolt directly to the generator, the exciter shaft, and that gets installed near the coupling flange of the brushless exciter where it gets coupled up to the generator rotor. So that the next few slides will go into detail a bit more about what that looks like. But the first part of this discussion will be on the EFRAM mid-shaft system for larger machines. So this is a cross section of what the coupling flange of the brushless exciter looks like on the right. And then the image on the left is the generator coupling flange, which is identical looking to the exciter. So they couple these 2 pieces together. And underneath that, there are what they call their butterfly leaf assembly, which is your field windings, your copper field winding leads are broken out on the back side of each coupling flange. So this gets mated together with this, and that's how they make an electrical connection between the exciter and the generator rotor. So we have to gain direct access to these field windings, and we do that by routing a threaded rod down through the bore of the coupling flange, and it gets screwed into the bolts that hold the electrical connection between the generator rotor and the brushless exciter rotor. So once that is done, we put some insulation pieces inside the coupling bore, and then we're ready to connect our rotating transmitter, which is this image here on the right. And we'll go into a bit more detail on what that looks like. So this is the EFRAM mid-shaft telemetry system. The inner green ring is the rotating transmitter. So that will be bolted directly to the brushless exciter and rotating with the machine. The outer ring is our stationary pickup antenna. So this is what's forming essentially those 2 hoops of wire, that rotary transformer connection between the rotor and stator. So the transmitter has a trace of wire that's connected or looped around the outer diameter of the rotating transmitter. And then the pickup antenna has a wire that is in a machine grooved and epoxied in place on the ID of the pickup antenna. So you can get an idea of the air gap between the rotor and stator, what we would usually see. It's about anywhere between maybe 15 to 20 millimeters of distance between the rotor and stator. So we're bringing data back across this air gap, which is our field resistance and field voltage. And then we're bringing an induction power signal across from the stationary world to the rotor to power the electronics that are mounted inside of this transmitter. So the transmitter is a high-strength steel collar that's machine specific to each customer's diameter size of their exciter shaft. And it houses an electronic module in one half of the collar, and then the other half has a weighted module for balance. So all of these systems are, we've done dynamic testing, balances in spin pit facilities, as well as static testing. So all of these systems are designed to be balanced and not interfere with any issues on the generator, on the exciter rotor. This is what the backside of the EFRAM midshaft transmitter collar looks like. You can see those two pockets I mentioned that house our electronic module to computate the data for resistance and for field voltage. And then the other module or the other pocket is just a dummy module for weight. And there it's split in half at the half joint here. And there's high strength bolts that come down and bolt these two half collars to the customer's brushless exciter shaft. And that would be specific to each machine depending on what the diameter of the shaft is. And we will provide a torque spec that these bolts need to be torqued down to hold the system in place. So those are the bolts that go through and connect the two half pieces together. There's a locking set screw for mechanical security that goes in and ties into the threads of the high strength bolt once it's been torqued into place. That's what it looks like installed on the customer's machine. So you can see our electrical connection that goes down through the coupling flange of the exciter and connects to the backside of those butterfly leaf assemblies where the field voltage windings are, and comes and sticks out on this end to connect directly to our rotating transmitter. So the customer's exciter shaft does need to be clean and free of any paint or rust or debris. So we have a good, strong mechanical and electrical connection to the shaft itself. Here's some more images of what that system looks like installed on a customer's machine. The image on the left shows you the rotating transmitter installed directly on the shaft. And then on the left side of that is the pickup antenna. So this would be in alignment. This would normally be moved over to the right and come into perfect alignment with the transmitter. And you can see that on the image on the right. We just wanted to show you for the image on the left what those two pieces look like installed on a customer's machine. And then the image on the right is what it would look like during final installation. So we provide the rotating transmitter component, the stationary pickup antenna, and then this mounting stand that's designed to be bolted directly to the brushless exciter floor and hold our pickup in place, and all the necessary hardware to mount everything in place is provided by us. That's what the pickup antenna and stand looks like. And this is just a 3D model to give you an idea. So those are the field voltage connections that go through the coupling flange. Then the transmitter collar pieces get installed on the exciter. The mounting stand gets in place, and then our pickup antenna is installed. And you can see the transmitter rotates with the shaft. Okay. Next, we're going to talk about our other system in the EFRAM family. This is electrically the same. It functions the same way as the EFRAM midshaft system. The only difference is it's a different mechanical package that's designed to mount directly on the end of a brushless exciter shaft, where we do have direct access to the end. So there's no permanent magnet generator. All your armature windings and diode wheel assembly for your brushless exciter are housed in one single compartment. and the end of the machine just has a cover plate, and the field winding leads come all the way through the generator rotor and directly into the brushless exciter rotor. And then there's an access point to get to those leads on the end of the machine. So this is a more simplified design. This is more common in your like GE style LM6000s, LM2500 style gas turbine generator sets that are maybe 40, 50 megawatts up to 180 megawatts or 200 megawatts, something like that in size. So smaller than the mid-shaft application. So on the end of the brushless exciter for these smaller gas turbine generators, there is when you remove the cover plate, you will see a piece that they call the rotor end cap. This is the only part of the machine that needs to be modified to house our rotating transmitter. And we will provide drawings and information on how to modify this. We basically need to have a hole drilled in the center of this rotor end cap so we can route the electrical connection to the field bus bars through the center of that. And you can see the bus bars kind of in the background here. So there would be a plus and minus connection to the field windings directly underneath this rotor end cap. So that's what that looks like. So there is your field windings that go down through the center of the brushless exciter shaft into the generator shaft, and then get wrapped around the generator rotor and many turns of copper bus bars. So there we drill and tap two small holes directly into the bus bars themselves, and we connect our plus and minus field voltage contacts on those bus bars. Then those wires get routed up through that center hole in the rotor end cap. We provide this aluminum adapter plate that's designed to pick up the bolt hole pattern on the rotor end cap. So that aluminum adapter plate gets secured directly to the customer's machine. And then we route our wiring into that adapter plate. And now we're ready to install our rotating transmitter. And that's what that looks like. So rather than a large collar that's split in half that we have to bolt to the outside of the brushless exciter shaft, we can mount this right on the end of the exciter, right in the center line. So this is like a snout. There's turns of wire that are cut on the outside of this snout. That's how we make our electrical connection and that rotary transformer connection between the rotor and stator. So the wiring gets landed directly to our transmitter, and the image on the right shows kind of a more finalized picture of what that looks like when it's installed. Next, we replaced the old cover plate. This would have just been a solid plate with no hole modified in it. So we replaced that with our own plate that does have a hole cut into it. And that allows us to house our stationary components to the system. So that's the center image here. This white ring is the stationary pickup antenna. So that gets coupled both radially and axially around that snout of the rotating transmitter. And you can see the air gap of communication. So the dark gray transmitter would be rotating with the machine, and this white pickup antenna is stationary. And then we just have to connect one BNC cable off to our receiver unit to receive the field voltage and field resistance values. And this is the same cable that we provide our induction power signal to power the electronics in our rotating transmitter. And then the image on the right kind of shows you a more finalized version. So everything inside the red circle will be provided by Accumetrics. The only thing we don't provide is the conduit that runs the BNC cable off to our receiver. That's a responsibility of the plant technicians or electricians to run a conduit for us to route our cable off to the receiver. So this is again showing you just an example on a 3D image of what that looks like. So then this is the stationary receiver unit. So this receiver junction box is the same for the F from mid shaft and the F from end of shaft, same electronics, same enclosure. You can see here, there are conduit routed directly into the enclosure. Again, that would be responsibility of the utility of the plant themselves. We need power brought to our receiver electronics, either AC or DC power. And then we always recommend that a single conduit cable be routed just for the B and C connection for the coaxial cable to the pickup antenna. So that's what this middle conduit is. And then the larger conduit on the left is your outputs, your relay, your 3 relay contact outputs, as well as your 4 to 20 current loop analog outputs would be routed back to the control room. This is the EphraimView software to give you an example of what that looks like. Basically, this is very normal. You can see the scattering of this resistance measurement that we're taking. This would be very normal on a customer's machine. We're taking a measurement, in this case, in this example, the software about every 40 seconds. So in every 40 seconds, that value of resistance does change slightly, and it's going to range from 10 megohms up to 100 megohms in this case. That's very normal and what we would expect to see. Over time, as that resistance value starts to drop and gets below about 500 kiloohms in value, this graph will become more of a linear chart, and you'll see a linear trend line of that resistance dropping. And then once it drops below the 100K threshold, it'll send you the warning alarm, and will allow you to kind of more closely monitor your equipment. And then as it drops further and gets below the 2 kiloohm threshold, it'll send the ground fault warning alarm. It also has the ability to detect for a malfunction alarm in the software, and we provide the field voltage resistance values, location factor, which defaults to this 222.2 when there is no fault, and then the field voltage value of the machine. There are some other details in here that we don't need to go to in great detail, but essentially some more troubleshooting ability is in the software information that we provide. All of our users don't use the EphraimView software to monitor their equipment long term. This is mainly used in setting up commissioning of the system. You can make some changes. You can change the threshold alarms to different values. If you wanted to increase your warning alarm value to say 200 kiloohms, you can do that. You can increase your ground fault alarm larger than 2 kiloohms. Some of our customers have chosen values like 50 kiloohms for the warning and 20 kiloohms for the ground fault. So we have the ability to change the thresholds of those alarms in the software. You can also make some changes to the time delay that's required to take each measurement. This customer chose to do it about every 40 seconds. Some customers choose to take a measurement about every 10 seconds. Again, that's up to each utility on what they would like to make those changes be. But again, the long-term monitoring is usually done with that analog output, that 4 to 20 current loop output, that the customer can trend in their control room for the values of resistance and field voltage over time, as well as monitor the relay output. So a lot of customers will just tie in the relays and tie in the 4 to 20 current loop into their control software. Okay, that's it for the ground fault monitoring product. Next, we're going to do a brief overview about our AT7800 AccuTemp system. So this is a system specifically designed to monitor 8 channels of RTD temperature measurement inside of large industrial motors. So that's what we're going to talk about next. So high temperatures can be significant damage to the wiring, the bearings, electronics, any kind of composite material inside of motors. It's one of the best ways to predict for failure is monitoring temperature, because if you're driving this motor beyond what it was designed to do, or you're driving it longer, you can create an excess amount of heat inside of the motor, inside of the armature windings of the motor. And over time, that heat can cause damage to your machine. So this is just giving you an example that a little bit is 10 degrees C can shorten the life of your motor by half. So the first step in preventing unnecessary shutdowns and extending the life of your motor is determining what the real temperature, real-time temperature data of that motor is during operation. Customers of ours that have used this system oftentimes are driving their motors well beyond what they were designed to do, in like a rolling mill application for steel or aluminum or pulp and paper, any large drive rolling type motors. The customers are driving those machines very hard. They're trying to get a lot of throughput through their plant and run these, 24/7, 365 days a year, continuous, and they generate a great deal of heat inside of the motor armature windings. And over time, that can cause significant damage and basically cut your motor's life expectancy in half. So it's very critical to know if you're getting hot spots inside of the motor and be able to monitor for that. So our system allows, again, the customer to gain access to the rotating armature windings of a motor, to detect those like transient temperature spikes or hot spots inside of the armature winding. It gives you real-time temperature data off these motor at all times. There are some systems out there that you can attach to a motor and monitor temperature, but you don't have direct access to them. You have to kind of go in during an outage, pull the device off, plug it into a laptop and say, oh, during this date, we saw we were getting really hot. I wish we knew that in real time. So the advantage of our system is it's a continuous monitoring device that's designed to be mounted to the machine while it's running, give you that temperature data in real time as the machine is on. So again, a lot of our customers, they just want to ensure that operational efficiency, long-term output of their machines, get that direct temperature monitor access on their rotor, and just be able to drive that throughput, drive that plant operation as much as possible, and just help know that they're preventing any excess damage to their motor. They really want to know what is the temperature inside this motor while we're running the unit. So the AccuTemp system that we have, again, has no maintenance needs. It's very easy to use. It eliminates the issue of any kind of mechanical slip rings that would wear and tear over time. It gives you that direct access to temperature inside of your motor. So this is an idea of what most customers would embed or use inside of the big industrial motors. These are RTDs. Usually the most common ones we see are like PT100 3-wire RTDs that are housed in these epoxy slots, basically, and those get installed inside the armature winding of the motor. And our system allows you to get access to that sensor data, that RTD sensor data. So this is what the AT7800 AccuTemp system looks like. It's, again, designed to work in very high noise environments that have a lot of EMI, RFA noise. We don't have to worry about any variable frequency drives or pony motors or lube oil pumps that are operating in and around that motor. Our system is immune to any of that electrical noise. We provide you with 8 channels of RTDs, and it's made up of these 5 main components: the transmitter collar, the antenna pickup, the induction power supply, the cabling to connect that then to our receiver assembly. So first, we're going to talk about the transmitter. Again, very similar to the EFRA midshaft system. It's a split collar design. This is manufactured out of a G10 composite material, which is a fiberglass embedded epoxy that's obviously non-magnetic, non-conductive. We have a trace of wire that's routed on the outside of this rotating transmitter collar, and then there's a stationary pickup antenna, which again has that turn of wire routed in that. This underneath this cover plate is the motherboard for the electronic modules for the 8 channels of RTDs. We provided this cover plate to, again, just give more protection of the electronic circuitry underneath. We don't have to dwell too much on this, but that I kind of touched on it in the last slide. This is just showing you, again, the stationary pickup antenna connection. And then this is our induction power supply unit. So this would be tuned specifically to each customer's application. We will do all the tuning in-house here in our lab, and kind of try and simulate real world environments. So we'll put the transmitter collar on a simulated shaft. We'll put metal in close proximity to the transmitter and pickup antenna to try to do a real world example of what the customer's motor may look like. And so once that is all set, we'll tune the induction power signal to match each specific machine, and then that's ready to go. The only thing that goes off from the induction power to the pickup antenna in the previous slide at this ring terminal connection is this twisted shielded pair that gets connected there. This is the cabling that goes between the induction power supply and the receiver electronics. Again, nothing super special there. And then this is our receiver unit for the AccuTemp system. It's housed on an 11 by 11 inch frame plate. Some customers choose to mount this in their own enclosure on site. You know, they may have another large enclosure that's bringing in sensing equipment from other parts of the motor, and they'll have access for us to put our electronics into that. Or we can provide this in its own standalone enclosure, similar to the EFRAM system like I showed before. It's had like a NEMA 4X style stainless steel enclosure, painted steel, whatever a customer may want to do. We have a lot of flexibility to put that in different types of enclosures. And then the receiver does provide you with a Modbus TCP output. This is kind of a more industry standard from customer feedback we've gotten, that they are used to seeing that 8 channels of temperature data come across on Modbus. We do have the capability to do digital to analog conversion and provide analog outputs on this system, but most of our customers have asked for that just as a Modbus TCP digital output. Okay, that's that. So I guess I'll open it up now for questions, if anybody has any.
Alguém tem alguma dúvida? Se quiser perguntar em português, a gente consegue passar para o Paul a questão e apoiar vocês aí com as dúvidas. So we have one question in chat, you can see.
Yeah, I'm just looking.
The question is, how is the size minimum for the application?
Yes. Is that for the EFRAM or for the temperature monitoring system? For the
Deixa eu ver the name. 1 minute, Paul. I did see the name of the customer here. Paulo.
Yes.
Paulo, sua questão é sobre o sistema para medição de temperatura ou sistema para medição de detecção de falha de aterramento?
Oi, olá, boa tarde, tudo bem?
Oi, tudo bem.
A minha aplicação, assim, eu trabalho com sistemas hidráulicos de grande porte. E eu queria saber se esse sistema pode ser aplicado para monitoração de motores, motores elétricos, trifásicos, na ordem de 100 cavalos para cima.
Ok. Paulo works using the big motors.
Você quer que eu fale direto?
Isso. Se você quiser falar inglês, não tem problema, pode ficar à vontade.
Ok. Hello, Paul. It's Paulo Bar speaking.
Yes, hello.
Hello. Paul, we have a company that works with hydraulic systems, okay? And in some application, we need to use large electric motors, 3 phases, okay? It's alternated current 3 phases. We want to know if it's possible to apply this product to monitor electric motor with minimum power is 100 HP is the minimum power. It's possible to do that?
Yes, we would need a bit more information as far as approximately shaft size of the motor rotor itself.
Okay.
Normally we see this request on much larger machines, 2,000 horsepower, 5,000 horsepower. But it could be possible. Yes.
Okay. Yeah, we have application too for mining metal equipment, and I think it's possible to apply these products to control or to monitor the big motors, the GE motors, GE motors.
Yes.
Okay, and they are using on the how can I say that in English? Is the
Pode falar em português que a gente apoia. em
moinho.
português.
Eu esqueci como é que se
Ball
fala moinho.
mills.
Ball mills. Yeah, ball mills. Yes. And we have some customers that they have ball mills, and they use the GE motors. I think it's 5,000 HP, maybe.
Okay.
Yeah, we can
Yes.
do that. We can apply that.
Yes, that would be much more in line with what we would typically see those requests for this system. That size
Okay.
machine. Exactly.
Okay. One other question is, actually, our customers, I request that the communication protocol needs to be made by CAN or CAN bus net,
Yes.
Yeah. Do
That's
you believe
possible.
that we have an option to communicate in CAN?
Yes, that is a possibility. Yep. There are interface modules. We've done things like Profibus, and I know there's a connection from CAN bus to Modbus. So that might just require a separate PLC that converts the Modbus output to CAN bus, but we can do that.
Okay, that's great. Could you please send to me the overall catalog as you can?
Yeah.
Yes.
Sure.
Okay. Thanks, Paul.
Yes, thank you. So we have another question come in about the maximum temperature supported for the AccuTemp system. Great question. Thank you. The transmitter electronics are rated to 85 degrees C. So I hope that answers your question. The stationary receiver board and receiver electronics are a lower temperature, but those would not be installed inside the motor housing. So they could be in a more climate controlled environment. But the components that go inside the motor directly mounted to the motor shaft are rated to 85 C.
Entendeu, Thiago? Isso, 85 graus. Alguém tem mais alguma dúvida?
Tem uma pessoa que fez uma pergunta.
Eu vi que o Thiago fez uma pergunta sobre a temperatura.
Ah, tá ali. O Paul respondeu, né?
Sim, respondeu. Bom, pessoal, se ninguém tiver mais nenhuma dúvida, a gente vai fazer as finalizações aqui. E caso alguém tenha dúvidas, queira alguma reunião, ou até mesmo uma visita técnica, o Paul estará aqui no Brasil. Nós vamos agendar uma data bem próxima. E nós podemos fazer essa visita técnica também na planta e tirar dúvidas aí da aplicação direta com vocês, tá? Oh, we have other question here.
Yes.
Let me see here.
Great question. So the EFRAM system does have ability. We do have another product that has the ability to monitor temperature as well. That is a system called a rotor health monitor system. It's designed in the same package as the EFRAM end of shaft unit. And that gives you the ability to monitor 12 channels of RTD temperature. But you can also use the more basic EFRAM system with a shunt current measurement device So we can connect the EFRAM to a shunt and measure the average field current flowing through that shunt, and that will be able to give you a prediction of rotor temperature as well. The customer, you'd have to have a shunt installed on the generator rotor, but we can do it by monitoring the average field temperature through current flow of a shunt or RTD temperature on a rotor health monitor system. Do you know what type of machine, what manufacturer machine you were talking about? Is it a GE unit or Siemens?
Consegue indicar para a gente? Okay, thank you. Thank you.
Siemens. Yep. Yeah, we've worked with Siemens Energy for a long time, many years. In Germany, they buy the two different styles of our rotor ground fault system, the mid shaft system and the end of shaft system, and both in both cases they use shunt measurement capability to give them average field temperature through a shunt current flow.
Mais alguma dúvida, pessoal? Bom, como eu estava dizendo, o Paul vai estar aqui no Brasil daqui a um ou 2 meses no máximo, a gente vai programar a visita dele. A nossa ideia com o webinar, além de apresentar previamente os produtos para alguns clientes, é justamente verificar aplicações aí, né, levantar leads interessados em conhecer melhor o produto. Se vocês quiserem, a Rufilda compartilhou aqui os meus contatos no chat. Podem estar em contato comigo diretamente no WhatsApp, e a gente pode agendar a visita técnica aí com vocês e verificar diretamente na aplicação. Oh, Thiago have one other question here. You can see this in chat, the question from Thiago.
Yes.
You have some photo?
I'd have to look for those. I don't have those readily available now, but we can supply some, I think.
You can send from me, and after I can share with Thiago.
Yes.
Okay. Thiago, o Paul vai enviar para mim. Nesse momento não tem nenhuma foto que ele possa compartilhar. Às vezes tem alguma informação ali que sigilosa de algum cliente. Ele vai enviar para mim uma foto de aplicação e eu encaminho para você.
Ok, Eline.
É o Thiago da IDB?
Thank you, Paul.
Ah, não, o Thiago da VEG. Ok,
Yes.
sorry. Any other question? Paul and Rufilda, I think we can finish our meeting. Rufilda, you can finish now?
Ok.
Ok.
Perfeito, pessoal. Muito obrigada pela presença de todos vocês no webinar. Eu espero que tenha sido muito proveitoso e que vocês tiveram conseguido tirar as dúvidas de vocês. Muito obrigada, Paul. Thank you. Perfeito. Então, todos que me enviarem as informações de vocês para realizar o certificado, vou estar enviando daqui a 2 semanas, mais ou menos. A gente vai estar entrando em contato com vocês. E caso vocês queiram enviar suas informações para mim, no meu e-mail, eu deixei no chat também. E o link desse webinar ele vai estar transmitido no YouTube. Eu vou compartilhar com vocês através do e-mail, quando estiver disponível, e também do grupo que nós temos no WhatsApp. Então, em nome de toda a equipe da MTS, eu queria agradecer novamente a presença de vocês nesse webinar. Perfeito?